Dear friends, it is lecture number 12, and today I will show you some tidbits of GeoGebra which are very helpful for understanding many other things. And so we start with the discussion and we go straight to the working table. And here I suppose sketch a function, any function, say sin x. Then my plan is to just produce a point on this sine curve, and the point will be always on the sine curve. It is not otherwise free. Whenever you create a point, for example, A, 1, 2, we know that it creates a point A here, 1. And this point in default, it is free to move anywhere. For example, wherever you take it and place it, the corresponding coordinates will be shown here. So it is a free object. Of course, I can make it fixed by going to its setting. But my point is that now I want to create a point, say P, on this sine wave. And if you try to move point P, it will be always on the sine wave. That is what I try to do. So how to do that? There is a very nice way of doing this. What you say that P will be a point, say equal to, and then you say it will be a point, and then this point on which curve, which function. The name of the function is f, so that is the sine wave. So P is created here. And if you try to now move this point P, which is P here, you will find it will always remain here. Okay. Now, why unnecessarily create a point on a function? It may look rather funny, but there are important things to do with this. For example, it is often necessary to find out the slope of a curve at a given point. So I want to find out the slope of the curve at this point. So in essence, we know that slope means you have to draw a tangent here at the point P like this, and tan theta of the angle that that line makes with the x-axis is the slope of the line. We know that. And the slope will vary because the tangent will be like this here. Tangent will be somewhat horizontal if you draw a tangent here, and so on. The value of the slope of the tangent will go on changing. Now, therefore, slope is a comment which is used to find out the slope of a line. It has nothing to do with function. For example, you create a straight line, say y is equal to, say, 2x plus 3, suppose. You create a straight line, okay, like this. Then this car, it is given an mg. If you write slope uh, of what? Of a line, which is g in this case, and you will get this nice triangle to indicate how the slope is calculated, and the value of the slope is denoted here. It is 2. Indeed, it is 2x plus 3. Y is equal to mx plus 3. M is the slope of the line, that is tan theta of this angle, isn't it? We know that. Therefore, slope is related to a straight line. That is what is depicted here. Anyway, if that be the case, we delete this. and also we delete this, we don't require. Okay, now my intention is to find out the slope of this function f at various points, and at various points the tangent line goes on changing. Therefore you have to draw that line. So first I will draw a straight line at various points which will be the tangent to this curve wave. So how to do it? It is done by a common tangent where at point P of what this point lies on the function f. And you see it has drawn a straight line. It has drawn a tangent to this curve f, that is the sine x curve. And this point, since I have restricted its movement on this sine curve only, you can change this point and get the slope or the tangent changes, the straight line changes at various points. Is not that? Therefore, this is a beautiful way of calculating, drawing the tangent to a curve at various points. And secondly, if you wish to find out the gradient at this point, that is dy dx at this point, the simple way I can do that at point P, at any given point P, draw the tangent and then calculate the slope of this line, that is G. That's all. Therefore, you simply say slope of G, and it is done. You put a return. So at this point P, the slope is negative. It is obvious, as you increase x, the value of y is decreasing, and the value is minus 0.6978, etc. And it becomes now dynamic. You don't have to do anything to find out the slope at other point. So you go on changing this. It will faithfully show the, it will draw the tangent at a given point P, and also it will show the slope of this line. Got the point? So it is an interesting way of doing this. Okay, now, after I have done this, I will do another interesting thing. And what I will do, I will clear all the things here for the time being. I don't want to save them. I have cleared them. Now, I will come back to ellipse. Okay. Eventually, I will try to find out the slope at any given point of the ellipse. That is my intention. Is now ellipse, as you know, can be why ellipse, circle also. You can draw it on this graph paper in various ways. So this time, writing down straight the equations, I will do it in a slightly different way so that you become very familiar with. There are many avenues by which you can sketch a particular object of definite equation. For example, this time I'll draw the ellipse in this way. Ellipse. Now, ellipse is having two foci, that is focus 1 and focus 2, isn't it? Two foci will be there, and so you can define the two focus. So what I do, I first draw any 2 points. For example, I draw a point, say A, at say anywhere I like. It does not matter. At point, say, oh, sorry, -2, 1. This is one point. and you create another point, for example B, B, and this point is say at 2, 2, 2, 2, comma 2, comma 2. So this is point B. Now, what my plan is that I want to draw an ellipse with these two as a foci, two focuses. And we know that if you define two focus points of an ellipse, the ellipse will not be unique. It is something like saying, I have fixed up the center of a circle. Will the circle become unique? No. Hundreds and thousands of circles can be drawn. And we also know from the planetary motions around the sun, Kepler's law say that planets move in elliptical paths with sun uh, as one of its foci. And all the planets have different orbits which are elliptical. Therefore, although the foci are same, but there may be many ellipses. So, just by telling that these two are the foci of the ellipse, I cannot uniquely draw an ellipse. So, to uniquely draw the ellipse, I must specify a point on the ellipse. Okay, I will specify a point on the ellipse. Say I define another point, C. Any point you specify, for example, you make it minus 1, comma, say 3, comma, say 3. And this point C is created. Now I say that to uniquely define the ellipse, I will say that A and B will be the foci and C will be on that ellipse. Okay, that is what I want to do. And for that, there is a beautiful comment. I'll go straight away to that ellipse and then I will specify its two foci, that is A, comma, B, and the third point says C, and this ellipse is drawn. Okay, that is fine. But mind you, this is the thing. If you move C, it will simply give you different ellipses. But C is not restricted to this curve alone. Let us check that because if I'm so sorry, why this point comes? This is it. Acha. Now what I plan, I suppose move C. Only thing ellipse will be different, but C is not uniquely moving on a particular ellipse. It is changing. Okay, this is the ellipse. Now what I will be doing, and once the ellipse is produced, it gives the equation of the ellipse in its this form. Okay, this is the equation of the ellipse, mind you. So it returns you the equation of the ellipse. Okay, now once this ellipse is fixed, I will now create a point on this ellipse, a general point on this ellipse. And this I know how to do it. I will simply say P is equal to a point on this ellipse, that is small c. So simply write small c. And it has created this point P. Now, if you move this point P, it will be always on the ellipse. That is the difference between C. So this C I need no more. I will just suppress it. So I have created a point which will move like this. You know. Acha. Another interesting thing, which is the property of the ellipse, the line segment PA, the length PA plus length PB, this will be always constant, no matter where P lies. That is the another definition of ellipse. Very interesting definition. And therefore, what I do here, I first draw a line segment, segment uh, between point P and the focus A. So it has joined this. Similarly, I create another segment, and I say that it is P comma B, and it gives you it returns you this length PB. Okay, so any point I have taken P on the ellipse, and I have joined these two focus of this ellipse with that. Okay, this we have done. Now, what I will calculate is the sum of the lengths PA plus PB. What is the sum of the length? It will be simply F plus G. That's all. That is PA plus PB. The sum of these two line segment lengths is 4.6. Yes, it is 1.6 plus some 3, 4.6 around that. So A plus G is the length of PA and PB. Okay. And let us verify that if you now change the position of P, which already I have created on C, it cannot go anywhere else. So you go on moving P to various location. The length of PA and PB changes. That is, F and G values becomes different. When P is nearer to B, this becomes less, this becomes more, no doubt. But look at A plus G, that is this length. Does it change as I move P? No. Although the value of A depends on P. So this is the property of the ellipse. If you have a point P here, you can move it around the ellipse, but PA plus PB will always, the sum of these two line segments will be always constant, and in this case it is some 4.65. Is that clear? Is it not very interesting? You can verify the properties of various functions if you know that property. Okay, so this is how it can be done. Now, what I will be doing is I will, as I promised you, I would like to see the I will try to draw the tangent to this ellipse at any point P. Say P is already there. I will try to do that. So this G and F, right now I don't require it after I have explained to you what I want to do. So it is there. Okay, so P is there. So once again, I want to draw want to know the value of the slope of the function which is described by the ellipse. I want to find out the tangent at point P to this ellipse. So I will first draw the tangent. So if I want to draw the tangent, I will have to simply write tangent. I will simply say it is um, at what point? At point P of what curve? On what curve? On which curve this point P exists? It is on C, small c. So comma, small c. And it has drawn faithfully the tangent at this point. And as you can see, if you move P, it will show how the slope is changing, is not? And tan theta of this curve will give you the rate of rise of y with respect to x at that point. And for that, what you have to do, because slope comment is with a straight line, therefore slope comment will be slope of what? Slope of the line tangent PC, which is given a name h. Small h is the length of the straight line. So simply write h, and it has given you the slope of the curve at the point P. And if you vary P, change the point P, the slope of the curve changes. Not only that, it also gives you the value of the slope displayed here. It displays the value of the slope at various points, is it not? Therefore, this is what is very interesting and very useful thing. That is, given a curve, you can produce a point, a general point on the curve, and the point will be confined onto the curve. And then, if you want to find out the slope tangent at that point P, you first draw a tangent and then find out the slope of that tangent line, and that will be in fact the dy dx at that point of that curve. Hope you have enjoyed this and learned something new. And so I stop here for lecture B, and see you in the lecture 13 with some more new things. Hope you have enjoyed the video. Thank you so much.